Okay, we're going to look at repeating decimals. These are decimals that do not terminate, but they do have a division pattern that repeats. And the repeat part is called the repetend. Okay, so if I'm looking at the fraction 5/18, let's see what happens. We could take the 5 divided by 18, because at first glance I already recognize that this is not going to be a terminating decimal because it doesn't have all powers are all prime numbers on the bottom, the denominator being 2s and 5s. It has these 3s as well. So I know that it's not a terminal decimal like we talked about in the 2 lessons ago. So we're going to work on dividing this to see what happens. So 5 cannot be divided by 18, so I'm going to turn this into tenths. So if I have 50 tenths, then that can split up, and we could get 2 in here, so that's going to be 36 of those tenths. That leaves me with 14 tenths. I'm going to turn those into hundredths. So if I have 140 hundredths, that can go 7 times. 7 times 18 is 126. We subtract and we get 14. We bring down 0, and look, we're getting 140 again. So that's going to again be 7. That will use up 126, and we'll keep continuing that. And you'll see that same pattern over and over again. So we'll keep getting that 14. So the part that's going to keep repeating is the number 7. So we're going to write that this fraction 5/18 is really 0.27, and we're going to write a little bar over the repetend, the part that continues to repeat over and over again. We're going to use a calculator for this next part just to see how this looks on a calculator. If I take 2 divided by 11, that ends up with 0.1818181818. But depending on how many digits your calculator can hold, it might have a rounded digit at the end. So we don't know if it's starting like a new pattern or what unless we actually did the division. But you can kind of see that that 2 is being rounded, is taking really a 1, rounding it up because of the 8 from what happens after it. So again, the only way to verify that for sure is to do the long division and see the pattern within the division that's repeating, like how we saw in the last one, how it kept having the 140, the 140, 140. We know that it's just going to be a bunch of 7s after. Okay, let's look at the fraction 1/3. 1 divided by 3 on a calculator ends up being 0.33333333. So again, you can see that that 3 looks like what's repeating, so that's the repetend. But on the calculator, again, it might be rounding off. We're not sure. The one way to check it, again, would be to that long division, but it looks pretty good here. Now, if we're given that a fraction is equal to this repeating decimal, we can use that fact to do to figure out some other decimals. So for example, 3/9 is really 3 times 1/9. So we know that that would be equal to 3 times 0.1 repeated, which would end up being 0.3 repeated. And then we look at the fraction 4/9. This is going to be 4 times 1/9, really. And so that's going to be 4 times that 0.1 repeated. So we get 0.4 repeated. Now on this next page here, we have a couple of statements that we're going to show with some examples why they're true. But first we have that a rational number may always be represented as either a terminating decimal or a repeating decimal. So if you have a number that cannot be written as a terminating decimal or a repeating decimal, then it's not going to be rational. And we'll talk about that next time, about irrational numbers. So if we have any fraction a over b in its simplest form, and b is bigger than a, in other words, we have a proper fraction because the denominator is bigger. Oopsie, proper fraction. And it does not represent a terminating decimal, which is meaning that the denominator is not just 5s and 2s, then the repetend can have at most b minus 1 digits. So the repeated section cannot be bigger than what the denominator is. So if we look at this fraction 1/7, what we're saying is that it can't, the repetend will not have more than 7 minus 1 digits, so 6 digits. So let's see if that ends up working out to be true and why that will happen. So if I take 1 and divide it by 7, again, I got to turn that 1 into tenths, so we have 10 tenths going on there. And so 7 can go into those 10 one time, and then that uses up 7. And so we're left with 3. And then we're going to turn those 3 tenths into hundredths, so we'll have 30 hundredths. That could go 4 times. We're left with 28. Now, just a reminder that as we're getting subtracting, we're ending up with these numbers here. They have to be less than the 7, otherwise it meant we could have gone an extra time. So let's kind of keeping that in mind. If I bring down a 0 again, change colors here, and we're going to go not 3, 2 times. That uses up 14, and then we have the 6. Again, that number is less than the 7. Bring down a 0. That's going to go a total of 8, which uses up 56. Then we're at 4 left over here. I'm kind of highlighting those for us so we can see what those remainders are. Then we're going to bring down another 0, so we're at 40, which will be 5 times. That's 35. Subtract, we get a 5. Bring that down. And then we're at 50. And then that will go 7 times to use up 49. And we'll have 1 left. That'll get me 0. Let's move this up a little bit so we can see them all. Oops, wrong color. Let's undo that. Trying to, again, highlight all of those remainders. So if we have 10, that's going to go 1 time. And that uses up 7. And then we have 3. And you can see we're back now to that repeated. Put that highlight on. We're back to that 3, and so it's going to continue to repeat. So the pattern that's repeating is the 142857. That's our repetend, and it has a total of 6 digits in it. And we could not have more than that because what's happening is those numbers that I highlighted, the 3, 2, 6, 4, 5, 1, those are the only possible remainders when we divide by 7, because if we had anything bigger, then we could go in a few more times. So these are the only possible remainders. Now if we end with 0, then we just would have a terminating decimal, and so you can see that as these continue on, we're the biggest possible repetition would be 6. Okay, let's see if we can figure this out again. So we're going to look at the fraction 2 over 13 now, and I want to take 2 divided by 13. So as I think about this division problem, the number of things that are possible for remainders are only 1, 2, 3, 4, 5, 6, all the numbers up to 12. Because again, as soon as I get to 13, I could have divided out by more. So that means I have 12 possible remainders. So as soon as I use up 12 things, that would be the most I could use up, and then I would have to be repeating. So I'm kind of running out of space here. I'm going to do this division problem, kind of move it over. We have, again, 13 going into 2. So this will turn into tenths. So we have 1, 13. We have a 7 as our remainder. Again, that's fine. We're having less than that 13. So we're going to go back to another 0 here, which will go 5 times. 5 times 13 is 65, which will give us 5 left over. Bring down a 0. 13 can go into 50. That would be 3 times. Use up 39, which will have us have 11 left. And again, keep continuing on, and you should be able to do this by yourself. Let's see when we start to repeat again. So 8 times 13 will be 104. We have 6 left. Bring down 0. So we're looking at, that would be a 4. To use up 52 of them, we're down to 8. Bring down a 0. So to do 80, that would be a total of 6 of them, which will use up 78. And we have 2 left. Still no repetition, so we have a lot of numbers that can go in here. So let's see, we'll have 4, 6, and then when we're at 20, which, oh, that does bring us back to the beginning. That would be 1. We have 13, and there's our 7 repeated. So you can see again that our remainders that we had were all these numbers that were less than 13. We didn't use up all of them. Then we start our repetition again. We didn't use up all the numbers less than 13, but again, those are the most number of things that we could have in our repetend. So we have 3, 6, 7 digits that are in there. And again, you could check these on your calculator, but when they start to be such big repetitions, it's kind of hard to see if that's really a repeated amount or not. So when I punch that into my calculator, it doesn't quite look like there's repeating, but I can see that it is from our long division. All right, let's try. We got one more here. Now this one, 18, that could be a long division problem because I can have a total of 17 possible remainders. And so this could repeat for a while. Let's see what happens. 18 going into 5, we'll say 5.0. I don't have that much space here, so hopefully it doesn't go on too long. So 2 times 18, that's 36. I'll be left with 14. Bring down a 0. That goes 7 times. We're left with 126. And we have 14. Woohoo! We're back 14 again. So we're going to keep repeating with the 7s. So we actually saw this earlier on the previous page. Didn't recognize that, but happy to see that it doesn't go in, have 17 steps in its repetend. So this is just 0.27 like we kind of already saw on the first page. But you could see I'll highlight again our remainder, but that's why you know that it's going to be repeating because we're going to keep getting that 14. Okay, so now we're going to go kind of the reverse way. If we have a repeating decimal, how do we go back and write it as a fraction? So there's a little bit of a trick to this, but the way that we start is saying, okay, well, let's let n be equal to that repeating decimal. And so then that means that 10n would be equal to 3.3333333. So it's kind of moving our decimal place over because it's saying we have 10 sets of this. So then if I take 10n, which is equal to 3.3 bar, and I want to subtract off the repeating part, so I'm going to subtract off an n. And so if I do that on the left side, I could do that on the right side, but I know the n was that 0.3 bar. So I'm going to subtract those. And so then that ends up being, well, 9n equals, and on the right side, that repetition cancels out. So we're just left with 3. So then we could divide that by the 9. And so we have that our n is 3/9, which could reduce to 1/3. So what we just showed is that 1/3 is really the n, which was 0.3333, which again, you could check that on your calculator. That 1 divided by 3 equals 0.3 bar. So let's try that again. We're going to let n equal 0.46 bar. So then this time if we did 10n, 10n would only be 4.64 bar. And we want to be able to like take away that repetition. So we actually want to look at 100n, which would be the 46.46464646. So then when we write 100n equals that 46.46 bar, we could take away that repetition, which was n. So take away that 0.46 bar, and it ends up that we'll have 99n equals, and you can see that repetition cancel out, we'll have 46. So then to solve this, dividing by 99, we end up that n is equal to 46 over 99. Which we could try and simplify that, but I don't think that simplifies. We have 23 and 2, and this is 3 times 11, so it can't reduce. So that would be my final answer. And so again, what we're saying is that this 46/99 is really equal to the 0.46 bar with repetition. And again, you could check it. If you take 46 divided by 99 on your calculator, 46 divided by 99, you should get 46, 46, 46, 46, 46. All right, we got one more for you. And now this one is kind of interesting. It's a little surprising, actually. And it's 0.9999999. So we can go through the same process as we actually did on the first one. And that is, we can say that let's let n equal the 0.9 bar. Since there's only one place value, we can look at 10n. We don't need the 100n unless there were two place values after the decimal. So 10n would be 9.9 bar. So if we set up our equation, 10n equals that 9.9 bar, and subtract off n, subtract off the repetition, we're going to end up that 9n equals 9. Divided by 9, we get n equals 1, which is a rational number, and it can be written as 1 over 1 if you want to see it that way. But look what we just said. 1 is equal to 0.99999999999. 1 equals 0.9999999. Isn't that so interesting? Okay, maybe just a little. And if you don't believe this way that we were doing it, another way to think about the 0.99 bar is to think about the fraction 1/3 we already know is 0.3 repeated. The fraction 2/3, you can punch that into your calculator or divide that, and you're going to get that that's 0.6 bar repeated. So just, again, this is just another way to see this very special equality. I could take 1/3 plus 2/3, and I know that that's 3 over 3, so that's 1. But look at this. 1/3 we said is 0.3 repeated. 2/3 is 0.6 repeated. That would be 0.9 repeated if you think about lining them up, right? 3, 3, 3, 3, 3 plus 0.6666. You're going to get 0.99999 repeated. So then what we're saying, you can see, is that same exact thing. That 1 will have to equal 0.9. All right, and that is repeating decimals.